Hello, and welcome to the Digital Spiffy YouTube channel. This video is the third in a series covering the material on the CCNP ENCOR exam. I will be using physical Cisco equipment to lab the material. The lab material is sourced from the CCNP ENCOR Lab Manual version 8. I highly recommend reading the CCNP Enterprise Core 350-401 official Cert guide in conjunction with this lab material. This will provide a better understanding of the labs and what is occurring on the equipment. You can find links to these books in the description below. This video will continue from the previous video in the series, which covers spanning tree. In this video, I'll dive deeper into rapid spanning tree and discuss spanning tree mechanisms. 802.1d spanning tree has scalability issues. Preventing forwarding loops at layer 2 works well with 802.1d, but only one topology is used. Larger environments with multiple VLANs need different STP topologies to direct traffic efficiently. Cisco created per VLAN spanning tree and per VLAN spanning tree plus to allow more flexibility than the original spanning tree protocol. PVST and PVST plus were proprietary spanning protocols. The concepts in these protocols were incorporated with other enhancements to provide faster convergence into the IEEE 802.1w protocol known as Rapid Spanning Tree. Rapid Spanning Tree protocol reduces the number of port states to 3. Discarding. The switch port is enabled, but the port is not forwarding any traffic to ensure that a loop is not created. This state combines the traditional STP states disabled, blocking, and listening. Learning. The switch port modifies the MAC address table with any network traffic it receives. The switch still does not forward any other network traffic besides BPDUs. Forwarding. The switch port forwards all network traffic and updates the MAC address table as expected. This is the final state for a switch port to forward network traffic. Rapid Spanning Tree Protocol defines the following port roles. Root port, a network port that connects to the root switch or an upstream switch in the spanning tree topology. There should be only one root port per VLAN on a switch. Designated port. This port will send and receive BPDUs with other switches. A root bridge will have all its ports with this type. Non-root switches will use this port type for ports connected to other non-root switches, as well as edge ports. This port type ensures that downstream switches have connectivity to the root bridge. Alternate port, a network port that provides alternate connectivity toward the root switch. Backup port, a network port that provides link redundancy toward the shared segment within the same collision domain, which is typically a network hub. Rapid Spanning Tree Protocol defines 3 types of ports that are used for building the STP topology. Edge port, a port at the edge of the network where the hosts connect to the layer 2 topology with one interface and cannot form a loop. These ports directly correlate to ports that have the STP Portfast feature enabled. Non-edge port, a port that has received a BPDU. Point-to-point port, any port that connects to another RSTP switch with full duplex. An efficient network topology has a specific switch designated as the root bridge, taking into consideration the hardware platform, resiliency, and network topology. Ideally, the root bridge is placed on a core switch and the secondary root bridge is designated to minimize changes to the overall spanning tree. Root bridge placement is accomplished by lowering the system priority on the root bridge to the lowest value possible, while raising the secondary root bridge to a slightly higher number. The priority value is a value between 0 and 61,440 and is modified in increments of 4,096. By default, a switch's priority is initially set to 32,768 plus the VLAN number it resides on. The best way to set a core switch as the root bridge is to set the priority to 0 and put the secondary root as 4096. Spanning Tree Protocol uses a cost system for root path calculation. The cost is based on the link speed of the interface. The route path is determined based on the cumulative interface STP cost. This cost can be modified to tune the route path. Spanning tree protocol also uses a priority metric on ports to determine a route port. The STP port priority impacts which port is an alternate port when multiple links are used between switches. The decision about which interface to use is based on the lowest port priority, which defaults to 128. Interface ID. The higher the port number, the less likely it will be the root port. The port priority can be modified in the interface config with the command spanning-tree port-priority number. The priority must be modified in increments of 16. In both spanning tree protocol and rapid spanning tree protocol, a new connected port must be guaranteed not to create a switching loop before it can become a forwarding port. This process can take up to 30 seconds, but can be reduced if spanning tree is configured with Portfast. An end-user device would not send BPDUs and could benefit from a quicker port transition. In rapid spanning tree protocol, ports connected to workstations, network printers, and non-switching devices are considered edge ports. Edge ports can safely enter the forwarding state right after they come up. Cisco developed a feature called Portfast that essentially allows you to define a port as an edge port. Any Portfast configured port will enter the forwarding state immediately after coming up, without going through a learning state. An interface can be configured as an edge port with a few different commands. The first two methods are in the interface config with the commands spanning-tree portfast and switchport host. The switchport host command enables portfast as well as statically setting the interface to an access port. However, this will break Ether channel ports, so check the port configuration before using this command. As discussed in the last video, Layer 2 does not use the time to live mechanism. This means that packets can be forwarded between switches infinitely if a loop exists. STP is used to prevent this, but there are additional features that STP uses in addition to root bridges and blocking ports to help prevent loops and tune network traffic. Root Guard is an STP feature that is enabled on a port-by-port basis. Root Guard prevents a port from becoming a root port. This is effectively used to prevent unwanted switches from becoming the root bridge. A root port is placed in an error-disabled state and considered as a root inconsistent port if a superior BPDU is received. This will prevent the configured designated port from becoming a root port. The port will be reinstated into its appropriate role and state automatically when it stops receiving superior BPDUs. Another feature of Rapid Spanning Tree Protocol is BPDU Guard. BPDU Guard is a safety mechanism that shuts down ports configured with STP Portfast upon receipt of a BPDU. Because Portfast causes an interface to go into the forwarding state immediately, there is a risk that a port connected to another switch could be mistakenly configured with Portfast and cause a loop. BPDU Guard will prevent this by placing the port in an error-disabled state. BPDU Guard can be configured globally or on a per-interface basis. BPDU Guard is configured on the global config with the command spanning-tree portfast BPDU Guard default. If this command is entered, the BPDU Guard will automatically be enabled on all Portfast configured ports in the switch. You can statically assign BPDU Guard to a port in the interface configuration with the command spanning-tree BPDU Guard enable. This command will take effect regardless of if the port is configured with Portfast. Neither Portfast nor BPDU Guard prevents the switch from sending BPDUs to an interface. BPDU filter can be placed on an interface to do just that. BPDU filter can be configured in the global config or on a port-by-port basis. If this is configured globally using the command spanning-tree BPDU filter default, the BPDU filter applies only to Portfast-enabled ports, and if the BPDU filtered port receives a BPDU at any time, the BPDU filter and Portfast will be deactivated and the port will become a normal spanning tree interface. configuring BPDU filter on an interface basis with the command spanning-tree Portfast BPDU filter, the port will stop sending and processing received BPDUs. The global configuration of BPDU filter is less desirable because it does not prevent ports from receiving and processing BPDUs. Rather, it only attempts to stop sending BPDUs on ports that are configured as edge ports. In a normal STP network, all ports receive and process BPDUs, even blocking or discarding ports. This is how switches know that the device at the other end of the link is up and superior. If a port stops receiving BPDUs from a superior switch, it will recalculate the root bridge. A typical fiber optic cable has two strands of optic cabling. A switch will operate with one strand to send and one to receive, and the switch at the other end of the cable will do the reverse. Network devices that use fiber for connectivity can encounter unidirectional traffic flow if one strand is broken. This can cause BPDUs to stop being transmitted. One solution for this problem is STP LoopGuard. LoopGuard prevents root and alternative ports from becoming designated ports if BPDUs suddenly stop being received on them. LoopGuard places the original port in an error-disabled state while BPDUs are not being received. This feature can be enabled globally using the command spanning-tree LoopGuard default or on an interface basis using the command spanning-tree guard loop. LoopGuard should never be enabled on Portfast-enabled ports. Before we begin labbing on the equipment, I'll refresh what has been discussed. STP Portfast, an STP feature that places a switch port directly into a forwarding state and disables topology change notification generation for a change in link state. RootGuard, an STP feature that places a port into an error-disabled state if a superior BPDU is received on the configured port. BPDU filter, an STP feature that filters BPDUs from being received across the configured port. STP LoopGuard, an STP feature that prevents a configured alternate or root port from becoming a designated port toward a downstream switch. We've covered the basis for rapid spanning tree and spanning tree features. Now we can configure our lab equipment and implement rapid spanning tree protocol and its protection mechanisms. If you are able to follow along with Packet Tracer, CML, GNS3, or physical equipment, I'll be using 3 Cisco switches and 1 Windows PC. In the first part of this lab, we will set up the network topology and configure basic settings and IP addresses for VLANs. I've saved the configuration in a text file and uploaded it to my website, digitalspiffy.com. You can find the link to download this and other related files in the description below. I've changed a few interfaces since the last video, as you can see in this network diagram. I'll start with configuring the D1 switch. In this lab, we will implement rapid per VLAN spanning tree. I'll configure the console port to prevent timeout and keep the logging from outputting over our terminal. We can now configure our trunk ports that connect to the A1 switch and allow the 2 VLANs used in this lab. The Gigabit Ethernet port 101 is a fiber connection that connects to the D2 switch. Basically the same configuration, but on a different interface. I'll configure the VLANs now and tell the switch to use VLAN 2 as the default IP gateway. The D2 and A1 switches will essentially be the same config, with the VLANs assigned a unique IP address in the same subnet. The switches have been configured, interfaces are up, and the spanning tree mode has been set. Our next step is to determine which switch spanning tree has elected as the root bridge. Using the command show spanning tree, on each switch we can see detailed information about the root bridge and which ports are used to reach it. The current root bridge was elected based on the lowest bridge ID, which consists of the priority, extended system ID equal to the VLAN ID, and base MAC address. If you want to know more about how this is calculated, watch the previous video covering spanning tree for Lab 212. So we've determined that D2 is the root bridge for both VLAN 1 and 2. We can tune this by modifying the priority on the switches. On D1, we will use the commands spanning tree, VLAN 1, root primary, spanning tree VLAN 2, root secondary. With this command, the priority is automatically set. The primary option sets the priority to 24,576 by default. If the root bridge priority has already been statically set, this command will lower the priority 4,096 lower than the current root's priority. This means the root primary command lowers the priority only as much as needed to win the root election. The secondary option statically sets the priority to 28,672. If you break out the calculator, you will notice that that's 4,096 higher than the current root option. On D2, we will do the opposite and assign VLAN 1 as the secondary root and VLAN 2 as the primary. Running the command show spanning tree root. On each switch, we can verify these changes have taken effect. So we've tuned the root bridges for each VLAN. Now we can adjust port cost values to impact root and designated port selection. Currently, there are two direct paths between the A1 switch and the root bridge for each VLAN. Path and port cost are evaluated to determine the shortest path to the root bridge. In the case where there are multiple equal cost paths to the root bridge, additional attributes are evaluated. In this case, the lower interface number is chosen as the root port, and the higher interface number is put in a discarding state. On the A1 switch, we confirm with the command show spanning tree and show spanning tree blocked ports. As you can see on A1, VLAN 1 has its root port on Fast Ethernet 01. Fast Ethernet 02, 3, and 4 are in the alternate role and blocking state. We can manipulate which port becomes the root port on non-root bridges by changing the port cost or priority value. On A1, I'll shut down the Fast Ethernet 01 interface and 02. I'll assign a lower port cost to the Fast Ethernet 02 interface. And then I'll bring the interfaces back online. Using the command show spanning tree VLAN 1. You can see that the port cost has been lowered to 12 from the default of 19. Fast Ethernet 2 is now going to be the root port for VLAN 1 based on the lower cost. This will also impact the VLAN 2 root port. Using the command show spanning tree VLAN 2, you will notice the cost to the root bridge is 16, and using the fast Ethernet 02 interface. This is because D1 has the gig interface connected to D2, which is the root bridge for VLAN 2. By default, the cost of a gig interface is 4, so 4 plus 12 is 16. This is less than what it would cost for A1 to use the fast Ethernet 03 interface to get to D2, which would be 19 by default on fast Ethernet ports. We can again adjust the cost value on the interface fast Ethernet 02 to 18. This will make the VLAN 2 root port fast Ethernet 03 again. The next method to impact root port selection is configured on the root bridge itself. In our current network topology, A1 has 2 connections to the root bridge for VLAN 2. The root port has been selected, in this case, based on the lowest port ID. Port ID is made up of 2 values, labeled as priority.number. As discussed earlier in this video, port priority can be changed in increments of 16. In the show spanning tree VLAN 2 command output, you can see the priority on each switch is the default of 128. Interface ID. On the D2 switch, we can modify the port priority of the fast Ethernet 02 interface, which connects to the A1 fast Ethernet 04 interface, using the commands spanning tree port-priority, and we'll set it as 64. We can make this connection the preferred port for the root path. On A1, running the command show spanning tree VLAN 2, you will notice the root port has now changed to interface fast Ethernet 04. The selection is based on the lower priority value of the D2 interface fast Ethernet 02, but you will only see this on the D2 switch. Previously in the video, we examined STP Portfast. With Rapid Spanning Tree Protocol, proper configuration of ports connected to host as edge ports is essential. Cisco switches default to all their ports being non-edge ports. On A1, we can enter the command to enable debugging output for spanning tree. And I'll bring up the port that the PC connects to on A1. You'll notice the output on A1 that the switch is trying to go through the proposal and agreement process, but because we have an end-user Windows machine connected to this fast Ethernet 024, it does not process BPDUs and has no need for spanning tree. On A1, we will get into the interface configuration, shut down the port, and make it a port fast with the command spanning tree port fast. You'll see this warning telling you that port fast should only be enabled on ports connected to a single host. And from the debugging output, you can see that Rapid Spanning Tree Protocol sees port 24 as designated quickly after doing the no shut command, and it never sends a proposal on that interface because we have configured it with port fast. And in the output of the command show spanning tree interface fast Ethernet 24, you will see that the port is now an edge port in the type column. In the next part of the lab, we are going to implement and observe STP protection mechanisms that were previously reviewed. Root guard prevents a port from becoming a root port. This is effectively used to prevent unwanted switches from becoming the root bridge. On A1, we can find a non-root port such as fast Ethernet 01, and enable BPDU guard. You can do this with the command spanning tree BPDU guard enable. And you'll quickly see that the port is going into error disabled. If we shut down the port, remove the BPDU guard, and then bring the port back up, and then we can verify the trunk is back online. BPDU filter can be used to prevent a switch sending BPDUs to an interface. On A1 we can see how many BPDUs have been sent using the command show spanning tree interface fast Ethernet 0-24 detail include BPDU. If we repeat this a few times, you'll see that this is increasing. You can also verify this in Wireshark as packets are received. Now let's configure the interface with BPDU filter using the spanning tree BPDU filter enable command. If we go back to the exec mode, and you can see that BPDUs are no longer being sent to the port. LoopGuard prevents ports from becoming designated ports if BPDUs are no longer being received. LoopGuard places the original port in an error disabled state while this is occurring. On A1 we can verify our spanning tree ports and see that fast Ethernet 01 is an alternate port. So let's configure LoopGuard there. And we'll use the command spanning-tree guard loop. Now we can stop sending BPDUs from the D1 switch on fast Ethernet 101. And I'll just use the spanning tree BPDU filter enable command. And it may take a second here, but on A1 we should see the output from the debugging indicating that LoopGuard has blocked port fast Ethernet 01 for VLAN 1. There you go. We can run the command show spanning tree VLAN 2, and you'll notice the port role has changed to designated. The state is in broken. In the type column there is text to show a loop inconsistent warning. After removing BPDU filter on D1 fast Ethernet 101, you should see that A1 fast Ethernet 01 port is in an alternate state after receiving a superior BPDU. Thank you for watching the Digital Spiffy YouTube channel. This video is the third in a series covering the material on the CCNP ENCOR exam. In this video we explored rapid spanning tree and implemented spanning tree protection mechanisms.